Hi and welcome back to a new video. Over 3 months ago, end of May, I was posting a video that I messed up. We made this direct dye cooler, and shortly after it was released to the market, we received feedback from customers that were reporting very bad thermals for both their CPU cooler and the heat spreader. We were surprised by it. I didn't really know what was going on, and I told you in the video that I didn't really know what was causing the bad thermals. But we quickly reacted and removed the cooler from the market to make sure there is no further spread and further disappointed customer out there. And now over 3 months later, we finally figured out what was the reason for the bad thermals for both cooler and heat spreader. And I want to talk you through our experiences, our learnings, and explain what happened. So this was our cooler, the one I talked about. Feel free to also watch the previous video. There you will find more information about what was happening or what was not working. Just a quick summary of how it works. It's a direct dye water block. So this surface right here in the center is the chip contact surface, sits on top of the chip, presses it down. At the same time, we have this ring right here that we call the pressure ring, and this ring presses onto the PCB right here to not only have the pressure on the core, but also on the PCB itself. Otherwise, the PCB would warp a little bit and you would have bad contact to the memory or no contact to the memory at all. At the same time, there's the challenge that these corners of the plastic socket are sitting higher than the chip in the center once it's pressed down, which means that if you press it down, you can't just have a flat cooler on top. It wouldn't work because it would collide with those edges. And that's why the area around the pressure ring, just the area around here, sits a little bit lower than the rest, simply to make space for the plastic part of the socket. I already told you in the previous video, in the first one, about this topic, that we were quite confident that we didn't really screw it up in the way how we designed the block, the dimensions, because I showed you cross sections and how we aligned the contact area to the chip itself to make sure that it has proper contact. But then looking at the results that we saw from the customers, it seemed like that this was not the case. And there were a lot of theories why that might be the result that we saw. And one theory was that the plastic socket of the motherboard would be outside the tolerances that we accounted for. So that the plastic socket would sit higher and would collide with the inner part of the water block, and then in result the water block not sitting low enough, not making enough sufficient contact with the chip to have good temperatures. And that was also something we wanted to test, if that's maybe the case, if that's maybe true. So we made some additional prototypes. We just made the outer area here a little bit deeper, about 0.4 millimeter, where we thought that should give us enough space to have the CPU for sure sitting directly underneath the block, having enough contact pressure. So we tried it with multiple prototypes, with multiple different mounting variations, different mounting pressure. And then after, 15 to 20 times mounting this cooler on this 14600K, the 14600K died. And I mean, that can happen with direct dye. It's unusual, but it can happen, right? But then we had a second 14600K, and we also had a 13900KS, and all of them died. After between 10 and 20 mounts, the CPUs died. And then I was truly concerned, because that is not normal. There are other direct dye blocks out there like Supercool or like Iceman, and none of them had this kind of behavior that if you mounted several times, that the CPU would die. So that was really unusual, and that seemed to be a different problem that I didn't even expect in the first video. So that's the dead 13900KS, and here we have the dead 14600K. If I just tilt the CPU slightly and you pay attention to the reflections and especially the corners, like this corner around the chip, just the corner of the PCB, you will see some imprints. Some imprints that were caused by the water block. We then put our CPUs underneath our LMX to do the visual inspection in much more detail. With a normal 3D scan, we can't really tell too much, but if we stretch it a little bit, then we can definitely see a difference. And we can not only see the imprint of the cooler onto the PCB, which is like in this corner and in this corner, but we can also see how it deformed the PCB overall. Like we have this convexity right here, it's a little bit concave on the area where the cooler pressed down, like here, and then again the PCB was coming up on the corner. Like the cooler was pressing down and then pressing the PCB down in this area, and then the edges of the PCB came upwards a little bit. So at that point we identified another problem where we previously didn't even know it existed. And it just happened because this ring right here, it's not even that high, it's like 0.5 millimeter in height, but it's made with normal CNC milling. So you have a 90-degree angle on the edge as a result. That's just normal if you do CNC milling. And what you do is you add normal chamfer, and we did a 45-degree angle to get rid of any kind of remaining chips and have a smooth edge. That's what you normally do with a CNC milling. But even if you add a 45-degree angle, there is still this defined edge. And this defined edge was pressing into the PCB, and if you mounted it with enough contact pressure and mounted it multiple times, and then this was causing the damage to the CPU. It was just pressing into the PCB. Then even we inspected this underneath a microscope, and we could see a cut in the PCB, probably damaged some kind of traces on the PCB and then damaged our 3 CPUs. That was kind of easy to solve though, because we just moved from a chamfer to a radius, and with the radius we don't have any edge at all. And we also tested this multiple times, and even no matter how often you mount it, with this radius doesn't damage the CPU anymore. So that was nice that we found why our CPUs were dying, but the performance was still bad. But we just moved upwards upstairs to my studio because light and audio is a little bit better there. Now we get to the interesting topic, and that is the nickel plating. At the time when we had all those performance issues and the issue with the dying CPUs, we also had issues with our supplier of the nickel plating of our blocks and also of the heat spreaders. It was just a typical issue, you know, communication problems. Then some of the parts we received back were scratched, and some just not nice looking surfaces. So at this time we were also trying to find a different supplier for our nickel coating. And then we had some samples sent to a separate supplier, and at that time they came back and we thought, okay, let's just do the visual inspection first, they looked nice, and then we tested them. And the ones we got back were 15 degrees Celsius worse than without nickel coating. And we were like, how's that even possible? 15 degrees Celsius, something must be wrong here. And there, at this point, I also have to admit, and I have to tell you, whenever we do development and designs in-house, we test without nickel coating. Because sometimes, you know, we do some kind of design, we mill it in-house, we have our own CNC mills, then we test it, and even at the same day we do some adjustment, we make another block and test it again, and maybe even a third one. That's just because we have in-house machining, we can do that quite quickly and efficient. I can't always do nickel plating at the same time, because nickel plating will take like 1 or 2 weeks with, you know, shipping to the supplier. He does the nickel plating, ships it back, you just lose some time. And if you want to be quick in development, you just skip that step. And that was our problem, to be fully honest. Because, yeah, we always thought that, hey, nickel plating doesn't really do much, right? At this point, we have to do a quick trip to material science and ask ourselves the question, why do we even nickel plate all our heat spreaders and coolers? Mainly because these are all direct die products, and for direct die, it's highly recommended to do liquid metal. Otherwise, you will lose a ton of performance and direct die wouldn't make a lot of sense. Now the thing is, liquid metal contains gallium mostly, as you probably know, and the gallium is corrosive versus most of the metals, especially copper and especially aluminium. Versus aluminium, it's terrible, but with copper it works, but it will degrade fast in performance. So if you don't nickel plate and cover the copper with nickel, then you will have a problem long term with the gallium corroding the copper. It will have a big impact on performance, and we want you to have a good performance not only on the first day but also after a couple of weeks and months, obviously. And that's why it's recommended and necessary to have the nickel plating to protect the copper. The go-to process for this, for the protection, is chemical nickel. There are generally 2 types. It's chemical nickel and electroplating. The chemical nickel means that you put those pieces of copper into a solution, and then with a chemical reaction you will have nickel particles sitting onto the copper in an amorphous structure. That is the main difference to the electroplating, where it's a crystalline structure. The amorphous structure has some benefits, and that's the uniform type of the coating, which also has a higher density, and due to the uniform particle distribution, it also has a uniform thermal conductivity, which is and can be a benefit. Due to the higher density, it also has a better protection, and this amorphous structure also causes the layer to have a higher density, and at the same time it's harder, and it just provides better corrosion resistance against gallium. The crystalline structure caused by electroplating, on the other hand, is softer. It has a defined crystalline orientation, and thus the thermal conductivity depends on the crystal orientation, how good and how bad it can be. And it's not as good as the chemical nickel when it comes to corrosion resistance. If you just Google, you would find that nickel has a thermal conductivity of about 19 watt per meter Kelvin and copper of about 390. That's just the theoretical value. You have to keep in mind though, whenever you have a coating on top of a different metal, there will be a contact resistance between the layer and the base material. And this contact resistance will differ from the process, from the type of nickel, from your supplier even. So that's hard to determine. A chemical nickel layer not only contains nickel but also phosphorus, and the amount of phosphorus determines different values such as hardness and also corrosion resistance. Typically it's divided into 3 sections. You have low phos, which is anything below 5%, 5 to 10% is typically mid phos, and above 10% is considered high phos. And the go-to process is typically the mid phos, so between 5 and 10% phosphorus in the nickel layer. This provides okay corrosion resistance, but it has a good impact on thermal conductivity. This low amount of phosphorus decreases the nickel thermal conductivity from about 90 to 40 to 50. So it cuts it in half. The other process, as I mentioned, electroplating. Again, you take your piece of copper, put it in the solution, apply electric current, and this deposits nickel particles onto your copper. But it's quite different in how the layer looks. In the chemical nickel, as I said, it's an amorphous structure. In electroplating, it's a crystalline structure. A crystalline structure has a much less adhesion towards the copper. And this results in a higher contact resistance between the nickel layer and the copper. On the other hand though, electroplated nickel is like 99% nickel. And this results in a much higher conductivity, thermal conductivity of the nickel itself. But as I said, you have a higher contact resistance between the nickel and the copper. So it's like a trade-off. We can also even calculate this, at least theoretically. And that's also what I did. And that's why I assumed that the nickel plating doesn't really do anything, because it's a very thin layer. So if we take this 3900 KS, it has about 250 square millimeters in area. Then we assume that we put an IHS on top, which is about 2 millimeter high with the same area, and it's coated by 10 micrometer of nickel. That's just typical. 10 micrometer will be sufficient when it comes to the corrosion resistance, and it doesn't have a huge impact on the temperature. At least that's what we assumed. And if you calculate it, the temperature loss that you have from the top of your chip to the top of your heat spreader is, if you just take bare copper without any plating, it will be 5.1 Kelvin with 250 watt assumed, which I think is realistic under load for a 3900 KS. If you then proceed with electroplating, it's 5.2 Kelvin, and with chemical nickel calculated, it's 5.3 Kelvin. So we lose, in theory, 0.1 to 0.2 Kelvin, calculated, in theory. I was also wondering if the layer that we ordered is as thick as we ordered, or if it's maybe 10 times as thick. So we did a cross section of our cooler, cut it basically, and then we looked at the nickel layer, where you can see that the result is 8.3 micrometers. And that's just in the expected range, because if we order 10 micrometers, it's given with a tolerance of plus minus 2 micrometers. So 8.3 is perfectly within tolerance. And you can also see that it's a quite uniform nickel layer, as expected, as we would like to see it. You can also see the resistance layer in between the copper and the nickel. So you can see some black dots, that's also expected, and that's where you lose a little bit of performance. That was quite a difference. Calculated 0.1 to 0.2 degrees Celsius difference, and we had 10 to 15. Then I remembered TechN. TechN is also a water cooling manufacturer. It's based in Berlin and we are about 10 kilometers outside of Berlin here. We're good friends with them and I knew that at this time we had the same copper supplier and we had the same supplier for the nickel coating. So I called Nick from TechN because we're friends and I asked, hey Nick, do you have any kind of experience with the nickel plating and how it impacts performance? And he was surprised and he said, there's not really any impact. It's below 0.5 degrees Celsius, so you can neglect it. It's like within tolerance. And I was like, yeah, that's what I assumed as well, but we see that it's not the case. We then also called our friends from Watercool and double-checked with them. They use different copper supplier and different nickel supplier, but they also confirmed to us they didn't see any kind of difference with nickel plating, but we did. The difference between TechN, Watercool and us is the application. We are doing direct dye. And direct dye, the cooler sits directly on the chip. The chip has a very high power density. So with 250 square millimeters on surface area, it's maybe only half of this what's directly dissipating the heat towards the cooler, because not everything of your dye is like the cores that are dissipating the heat. So we can, from that 250 square millimeters, maybe assume that about 100 square millimeters are directly emitting the heat towards the cooler. And if you compare this with an Intel heat spreader, this is about 1,100 square millimeters in surface area. So it's more than 10 times as much. That means that the difference for nickel plating is more than 10 times less if you just apply your cooler to the heat spreader versus direct dye. So on direct dye, it's just much more relevant. In the end, our entire design, everything was fine from the beginning. It was just that we failed in our validation process, in our testing. That was also caused by one CPU dying during this validation process. So if you have two 14600Ks, they will perform different. They will have different temperatures. Might be different by like, I don't know, 5 degrees or like 10 degrees between two different CPUs. And we didn't test it fully again. So we should have taken a second CPU, do the entire process of measuring without delidding and then delidding and check all the temperatures. Then we would have noticed that with nickel plating, the performance would be off. But we had without nickel plating on one CPU that died, and then with nickel plating on a different CPU, which was not comparable. And this is how we messed up. After all that, I was in contact with, I think, about 20 suppliers of nickel plating. And then out of those, we identified 5 that we might want to work with. And we did a lot of orders with test samples. That's just a few of them. So for example, that's electroplated nickel. This is a nickel chrome layer. And this is chemical nickel. And this right here is what we went for. And you will see that it looks a lot worse. That is the downside. Like, this is so nice, like the reflection, it's perfect mirror finish. I would love to still have this, but unfortunately, this is the one that performs by far the best. And as a company, Thermal Grizzly, performance for us is the most important. So if it looks worse, that's unfortunately how it is. But from our current testing, this type of nickel coating will just work by far the best. This with the chrome plating was also quite interesting. You might ask why we didn't go for chrome plating, because in theory chrome is even better when it comes to corrosion resistance versus gallium than nickel. However, you can't really deposit chrome directly on nickel. It doesn't stick. The adhesion is quite bad. So you always have to get a nickel layer first. So you get a thin nickel plating and then you put chrome on top. And that in result, because you have 2 times resistance layer, like boundary between the layer, the coating and the copper, yeah, it just doesn't perform that nice. During this entire process, we obviously also made different changes and different progress, because we have not been in the water cooling business for that long. It's a bit over a year and we had to learn a lot when it comes to also manufacturing. For example, that was the structure that we were working with, let's say, half a year ago. So the cooler that we went or removed from the market originally, our original Mycro, was this one. And it was featuring this cooling structure with 0.5 millimeter slotting. So the mill that goes through here is basically 0.5 millimeter wide. And here you can see different prototypes that we made during that time. And we figured out that we can make a much better structure. And all of these are with 0.25 millimeter slotting. That means the surface area on these potentially is a lot better than on this one. And that also, yeah, is much better for performance than the old block, which means that we just decided to just discontinue this product entirely and just make a new one from scratch, have this with better performance, fix the nickel plating, and also at the same time we improved the structure and the performance a lot. So that's the final cold plate, as you can see right here. And interestingly, if you compare it with the previous one, this is much wider when it comes to just the raw surface area. But if you look at this one, it also has a slot in the center right here, and the fins are a little bit lower. So I think overall the surface area is not much different between these, but with those optimizations, more fins and shorter, you have higher flow rate on this one than on this one, and due to the fins sitting closer together, the resulting performance is just a lot better than this one. So yeah, that is the updated cooler, the Mycro Direct Eye Pro. Comes with all the fixes, the improved nickel plating, much better surface area, and yeah, featuring this with 0.25 slotting. The final cold plate now is with electroplating. So we changed from chemical to electroplating. It is a little bit worse when it comes to corrosion resistance, unfortunately, but the temperatures are just so much better in reality. And also on this specific sample, it doesn't even look too bad. To avoid further disappointment, we then decided to send about 10 samples to other enthusiasts and previous customers for them to double check the cooler for us and give us feedback. So mainly, yeah, thanks to people on overclock.net like LeonMan44, Ovic84, Carillo, people who were willing to spend their time testing the product for us, and they also reported back really good results. I will link it down below in the description. Some results were like 3 to 4 degrees Celsius better than like a super cool or an Iceman block, which in the water cooling scene is quite a lot. And yeah, I'm happy that we finally made a product that is working, that is performing fine. Even though we are very, very late to the party when it comes to socket 1700, it's late, but it's never too late to learn. And we obviously took all those learnings, improvements already to the next generation, already preparing the Aero Lake water block. And yeah, I hope you enjoyed this video. This block is finally up for sale. You can find it hopefully locally or also in the Thermal Grizzly store. Thanks for tuning in, and yeah, thanks for listening to all my theory and blah blah. See you next time. Bye bye.